All right, this is your fourth and final vectors lesson, and it's actually also your last new lesson in Math SL for the last 2 years. So congratulations if you've made it this far. In today's lesson, we're going to be looking at applications of vectors. Again, it's just going to be putting a lot of the theory that we've already learned into practice and applying it to some practical problems. A lot of the problems that we are going to be solving with this will involve some kind of objects colliding, as can be seen on the by the picture on the front slide here. We have Snoopy and the Red Baron. They each have a vector equation for their paths, and again, you'd obviously be interested to know whether or not they will collide, and that's what we'll be able to find out throughout today's lesson. All right. So the first thing we'll do. Start with the first problem here. The first applied question is, so there's a couple towns, and again this could be a way you could apply vectors. 3 towns are joined by straight roads. Oakham is at the state capital and is considered as the origin. Axthorpe is 3 kilometers east and 9 kilometers north of Oakham. Bostock is 5 kilometers east and 5 kilometers south of Axthorpe. If we use the vector basis of I being 1 kilometer east and j being 1 kilometer north, what we want to do is we want to find the position vector of Axthorpe relative to Oakham. What may be beneficial to do at this point too is just to draw a picture of the situation that we have. So Oakham is the origin, convenient choice of first letters. Axthorpe is 3 kilometers east and 9 kilometers north, so it might be positioned up here. And Bostock is 5 kilometers east and 5 kilometers south, so that would be a further 5 east and 5 south, so Bostock might be positioned there. And so the first question, we can put position vectors in for these. Axthorpe is 3 east and 9 north, so its position vector would be 3, 9. We'll actually probably find B later, but we can also probably find it this way. It's 5 east, so 5 further east and 5 south. So its position vector can be given as 8, 4. Add 5 to 3, subtract 5 from 9. So its position is 8, 4. All right. And again, we have basically have a bit of a triangle here. Okay. All right. The first question says, find the position of Axthorpe relative to Oakham. So really what we're finding is we're finding vector OA, the position vector of Axthorpe, which we've already identified as 3, 9. In part B, it says find the position vector of Bostock relative to Oakham. So really what we want here is we want OB. We want position vector OB. And if we use some of the position vectors that we've talked about before and some of the addition principles, we can do that by going from OA to AB. All right? And AB is simple. So OA, again, given in part A above, and AB is just going to be 5 right and 5 down, and that's going to give us the vector 8, 4, which we already identified at B, but this is a formal calculation. And then, so we've answered A and B. The next part, in part C, tells us, first of all, there's a bus stop that's situated 2/3 of the way along the road from Oakham to Axthorpe. We want to find the vectors OS and BS. Right. So, S is maybe somewhere in here. Okay. So, we want to find OS, and we want to find BS. Like that. Okay. Go to the next slide. The next slide's open. Some working. All right. So we're told in the question that OS is equal to 2/3 of OA. It's 2/3 of the way from Oakham to Axthorpe, so it's 2/3 of the vector from O to A. And that's just a scalar multiplication, 2/3 of 3/9. And that is 2/6. I'm sorry, the vector 2/6. We're also asked to find vector BS, which again, using our vector addition principles, lettering-wise, algebraic, we can go BO plus OS. And it'd be nice if we could get B as a position vector, so that would be the negative of OB plus OS. And again, usually we like to write it as a subtraction, so we might write this as OS minus OB. Again, that's a formula that we should know from before. The vector OS is 2/6, the vector OB is 8/4, and we do the subtraction, and we get the vector negative 6/2. Alright, that's the vector BS, and that's from B to S. And then the question D, so this is basically question C. The question D asks the question, prove that the bus stop is the closest point to Bostock on the Oakham to Axthorpe Road. If a point is the closest point to a line, the thing that you have to know, and again you might have seen it or heard it before, is that it must be the perpendicular distance to that line. So essentially what we're saying is if S is the closest point, if S is the closest point to B, then BS should be perpendicular to OA. And if that's true, then BS dotted with OA should be 0. So the vector BS that we found, negative 6/2, dotted with the vector OA, 3/9. Again, we're using this as a proof. We're testing to see if this is going to be true. So it's going to be negative 6 times 3 plus 2 times 9 equals 0. So that's negative 18 plus 18 equals 0. Obviously that checks. And so then we could say that BS is perpendicular to OA and the closest point. Okay? All right, moving on. The relationship between speed and velocity in vectors. The note here is that speed is the magnitude of velocity. Okay? So again, if a vector equation is representing the velocity of an object, you need to find the magnitude of the B vector. Again, the B part is the vector. You need to find its magnitude. So for example, if we have an object with this vector equation for its movement, we know that it's starting its movement at 2, 0. It has a velocity vector of, its velocity vector is the B vector, 1, 2. And the speed is the magnitude of the velocity vector, so it's the root of 1 squared plus 2 squared, which is the root of 5. And that would be in whatever units, kilometers per hour, meters per second, whatever's given in the question. And this question has no units. This next question, all right, so we have a velocity vector and the speed of an object. So you want to find the velocity vector and the speed of an object with its position defined by 1, negative 1, and t, 3, 4, all right? Where the unit vectors represent 1 kilometer in each of those directions, easterly and northerly, and the parameter t represents the time in hours. Describe the motion of the object, okay? So we know that object starts starts at the point 1, -1, like this. We know that its speed is equal to the root of 3 squared plus 4 squared, which we should know is 5, and that is in kilometers per hour, the units in the question. Okay. And if I was describing this object's movement, I might want to put it on the coordinate grid. I know it starts at 1, -1. It starts down here, and its vector is 3, 4. Like this, so 3, 4. So I could describe its motion using bearings. So I might say I would want this angle in here, theta. Okay, and so I would say tan theta is equal to 4/3. Theta then works out to be 53 degrees. Right. And again, giving it as a bearing would be from north. All right, and so we could describe the object's motion as just say the object starts at 1, -1 and moves at 5 kilometers per hour. 5 kilometers per hour on a bearing of 37 degrees. And that would describe the object's movement. All right, let's carry on. Number 3, question number 3 here. We have a couple parametric equations, all right? And if you'll notice, it's x is equal to 4 plus 5t, y is equal to 5 minus 2t. If you write them kind of above each other, 4 plus 5t, y is equal to 5 minus 2t. You might recognize that this is basically the vector form. Right. So we could write it like this. We could write it as xy is equal to 4, 5. So everything x is on top, everything y is on the bottom, plus, and then put the parameter t outside the movement vector, and then we have 5, -2. So it can be represented in vector equation form, just like that. Now the question says, what is the object's speed? That's what I was talking about before. So if you want to take the speed out of the vector equation, we take the magnitude of the b vector. So in this case, speed is equal to the root of 5 squared plus -2 squared, and that is root 29, which could be approximated to 5.4, and this time it's meters per second. And now here's the classic type of question that you might be asked. It says a pole is located at the point 39, -9. Will the object collide with the pole? So now what we're going to do is we're going to use the vector equation of the line, the one that we wrote here. And really what we're finding now is we're finding out if 39, -9 is a point on this line. The concept or the idea that we're going to use here is that position vector r, the general one, can be represented by any point on the line. So I'm going to put this point that I'm interested in, I'm going to put that in for r, or for xy. So it would look like this. So in part C here, I'm going to test with 39, -9 to see if it's a point on this line. And the question I have to ask is, how will we know if 39, -9 is a point on the line? Think about it for a second. So if we just start writing equations here, we get 39 is equal to 4 plus 5t. I can solve this one. This is 5t is equal to 35, and t is equal to 7 then. And on the second equation, would be -9 is equal to 5 minus 2t, and then we get 2t is equal to 14, t is equal to 7. Notice what's happened here with both of these. The parameter t is worked out to be the same value, and if that happens, then that point, the position of that object, is on the vector equation of the line, or it's in the path of that object, because both components have the same parameter, and that's necessary in order for that point to be on that line. Hopefully it's obvious to you that if both of these parameter values were different, you'd be moving different amounts in the x and the y direction, which is not possible. Once a parameter is chosen, it has to be applied to both components. All right. And so the conclusion that we can come to here is that, therefore, the object will collide with the pole. All right. And it's because both components have the same parameter value. Oh boy, we're already at 16 minutes. Okay, let me try and hurry here. All right, and then one more question, same kind of question, will the objects collide? But now we have two objects, both defined by vector equations. And so, again, the idea is the same. Again, don't forget that r can be represented as xy and as xy as well. And so now if they collide, their vector equations have to be equal. So we would say -8,3 plus t 4,3 has to equal 2 -7 plus t 2,5. As long as both objects are starting from the same time in a kinematics type question, it's okay to use the same parameter. If they don't leave at the same time, you should use different parameters. And also in the case of any geometric shapes, you should use different parameters. All right, so we'll just write the equations across each row of the vector. So -8 plus 4t is equal to 2 plus 2t, and 3 plus 3t is equal to -7 plus 5t. Again, we can solve either of these equations, but it might be worth it to do both. From the top equation here, you should see that it'll end up solving as 2t will equal 10. So t is equal to 5. And the bottom equation, likewise, we get -2t is equal to -10. So t is equal to 5. And again, the parameter is the same in both cases. Now if we want to find at the location that they'll collide, again we can go, this is part B if you want in here. We can say xy has to be, and again we can use either equation. So this is 2 -7 plus 5 times the vector 2, 5. So this location xy will be 2 plus 10, 12, and -7 plus 25, 18. And so they will collide at the point 1218, or position vector 1218. And that's it for vectors 4. Congratulations. See you in class.